Thank you very much to the organizers for giving me the opportunity to speak here. And of course, a big happy birthday to Stephen. It's a real pleasure to be here participating in this conference. I'm going to be talking about a recent paper, collaboration with Juan Maldacena and his student Zhenbin Yang. This paper, in turn, was following up on a really exciting development last year, a paper by Gao, Jafferis, and Wall. The two-sentence summary of the talk is that wormholes in general relativity can be made traversable by a simple coupling of the two asymptotic regions. And this is useful as a simple model for how information can escape from black holes. I want to emphasize that this is not useful for space travel. The application here is a theoretical application to try to help us understand black holes better. So, okay, this is the plan of the talk. It's going to be pretty much a normal research seminar. Maybe the only unusual thing is there's going to be a lot of pictures. Okay, we're talking about wormholes. And I'm going to start by reviewing some properties of a very simple wormhole, which is sometimes called the thermal field double black hole. This is the Penrose diagram for the maximally extended ADS Schwarzschild black hole. So this is a normal black hole in anti-de Sitter space. And it has two asymptotically ADS regions, this one here on the right and this one on the left. And they're connected by a wormhole. That wormhole collapses to a singularity in the future and in the past. And we have these two horizons, the dashed lines, that separate the spacetime into four regions. This is the right exterior, the left exterior, the past interior, and the future interior of the black hole. So one of the reasons for thinking about this in ADS is that we can think about this also in terms of ADS CFT. And in ADS CFT, we interpret this geometry as a particular state in the Hilbert space of two copies of the CFT. We have two copies because we have two asymptotically ADS regions. And the particular state looks like this. It's called the thermal field double state, and it's a sum over all of the energy eigenstates in the left system, tensored with the corresponding energy eigenstate in the right system, and weighted by the square roots of the Boltzmann factor. This is a particular quantum state in the tensor product of the two CFTs. So here, I didn't know what type of picture to draw for strongly interacting CFT. So here we have a stupid picture, some boxes of particles. And what this is supposed to represent is that we have these two systems, and this line is supposed to represent the entanglement. This is a very highly entangled state between the left and the right systems. It's important to note, though, that although they're entangled, these two systems are not interacting with each other. So their time evolution is just decoupled Hamiltonians on the two systems individually. Something which obviously follows from that is that if we make a perturbation to the right system, indicated by this red stuff here, that might rattle around in the right system, but it can't affect the left simply because the two are non-interacting. Now, this is an obvious property of the quantum mechanics description, of the CFT description, and we should check it also in our gravity description. So if we make a perturbation to the right side, that would be like acting with some operator near the boundary here. That creates some kind of a disturbance which can propagate into the bulk. But you'll notice that it's separated by a horizon from the left boundary. So it's not possible to act on the right side and send a signal to the left asymptotic region. In other words, the wormhole is not traversable. And the fact that it's not traversable is reflected in the fact that perturbations to the right system remain in the right system. They don't propagate to the left because those systems are non-interacting. There's something that might make you a little bit uncomfortable about this, though, which is that this property looks extremely robust on the quantum mechanics side. It's just because the Hamiltonians are decoupled. But it looks a little bit delicate from the perspective of gravity, because if we move this point down, it looks like it's almost going to make it to the left side. And you might worry that if we perturb the geometry a little bit, it will now be possible to send signals from the right side to the left. But actually, a little bit of thought shows that it's robust on the gravity side as well. So let's consider a simple case to illustrate the point. Let's make a perturbation to the left side of this system. So now I'm drawing the new geometry that we get after we make a perturbation at time tw on the left system. That adds some kind of a disturbance, this green wavy line that propagates into the bulk. And that matter might backreact on the geometry a little bit, and the backreacted geometry is no longer a square Penrose diagram, it's a diagram like this. The important feature is that these two horizons no longer coincide with each other. They're separated by delta x plus in this null separation. Separation is proportional to g Newton because it's a backreaction effect. And it's also proportional to a component of the momentum of the matter that we threw into the black hole here. We can write that as an integral of the stress tensor along a slice like this, the null-null component of the stress tensor. And this is a quantity which is positive by the average null energy condition. So the point here is that delta x plus, the separation of the horizons, is positive. That makes it even harder to send a signal from the right side to the left. And in other words, what's happening is this average null energy condition, which says that this operator is positive, makes this property robust on the gravity side as well. So this resolves this tiny tension that we had on the previous slide. Okay, I also drew a second diagram here. This is the type of diagram that's going to be useful later in the talk. It's supposed to represent exactly the same geometry as this diagram, but in discontinuous coordinates. So the rules here, we continue to draw a square, but a continuous trajectory, when it crosses the matter here, jumps. It jumps by an amount delta x plus in the null direction. So these types of diagrams are going to be useful in what follows. Okay, there's one other comment I want to make about this thermal field double state, which has to do with the structure of correlations in this system. This is going to be important. As an almost defining property of this thermal field double black hole is that it has a large degree of local correlation between simple operators in the left system, let's say at t equals 0, and corresponding simple operators in the right system at t equals 0. The explanation for that is just that these two asymptotic regions are close to each other through the wormhole, so they have a lot of simple local correlation. But we can also ask what happens when we perturb the system a little bit. So if we look at this perturbed state where we added some matter here, the geometry is a little bit different, and the left and right sides are actually farther away from each other now. The correlation between the two sides is decreased. If you work this out in a little bit of detail, what you find is that, let's say, the two-point function of these operators here in the state with the perturbation, that's the green angled brackets, divided by the unperturbed two-point function, just in the thermal field double state. Well, this thing looks like 1 and then minus a term, which is small because it's due to a backreaction effect. The increased distance is a backreaction effect, so it's proportional to g Newton. But it's also proportional to this growing exponential of the time difference between the place where you insert this operator and t equals 0. So this can have a large influence if the time becomes of order the scrambling time, which is logarithmic in 1 over g Newton. This has been recognized as a symptom of chaos in the boundary theory. So in the bulk, the explanation for it is that if we push this point down farther and farther, because time evolution in a black hole background is like a Lorentz boost, the energy of these particles becomes very large in the relevant frame, and so the g Newton times energy backreaction becomes large. The explanation of that in the CFT is that we've added a few particles, but we've waited long enough that the chaotic nature of time evolution will allow those particles to have a big influence on the state. Okay, so the next little piece of background material I want to discuss has to do with negative energy in quantum field theory. So we saw that because of the average null energy condition, we couldn't send signals from the right side to the left, but if we could somehow get negative energy, we would be able to do that. So it's possible to have negative energy density in quantum field theory easily. So let's discuss that first. So I'm going to think about maybe the simplest case to discuss, just a massless scalar field in 2 dimensions. The scalar field is called capital O, and that's the action for it. And we're going to consider this state here. So the state psi is given by acting with this operator e to the ig O left times O right on the vacuum, where O left and O right are the field operator O evaluated at these two space-like separated points, let's say on the t equals 0 slice in the 2-dimensional Minkowski space. Okay? So that's the state psi, and what we would like to evaluate is the expectation value of the stress tensor in that state, let's say the 0, 0 component of the stress tensor, so the energy density. Now you can evaluate this by plugging in this expression here and then expanding in powers of little g. At order g to the 0, we just get the vacuum state where the expectation value of the stress tensor vanishes. At order g, we have a term involving the commutator of this operator with the stress tensor. Let's imagine that g is small so that the linear term in g is the most important. Well, it's not hard to work out this commutator using the commutation relations of this free massless field. In particular, the commutator of O with the derivatives of O that appear in the stress tensor are delta functions. They're localized on light cones. So you can work this out. Rather than writing an equation, I'm just going to draw the configuration of positive and negative energy density that you get in this state. So the blue lines represent regions, delta function localized regions where we have negative energy density, and the red lines are regions where we have positive energy density. This is assuming that g is positive. If g is negative, then of course it's the opposite, because this term was just the linear term in g. So we can imagine now computing this average null energy quantity by integrating the minus minus component of the stress tensor over this infinite locus here, this dashed line. That gives us p plus. And, well, that's 0. It's 0 because of a cancellation between a negative term here and a positive term here. Now, you could actually have anticipated that this would be 0, because whatever we find is at linear order in g, so it's proportional to g. So suppose we had got a positive answer. Then we could just change the sign of g, and now we'll have a negative answer, and that would violate the average null energy condition. So this has to vanish at linear order in g, and indeed, it does vanish. Okay, so far we've been thinking about this state as, well, we wrote it in this way as some operator acting on the vacuum, but we thought about it as a state just evolving with a time-independent Hamiltonian. There's a related thing that we can think about, which is we can consider a different history, where we start with the vacuum. We start with the vacuum state evolving with the normal Hamiltonian, and then at time t equals 0, we interrupt the evolution of the system by acting with this operator e to the ig O left times O right. That's like adding a time-dependent term to the Hamiltonian, which turns on at t equals 0. And then after that point, we let it evolve with its own normal Hamiltonian. So after that point, we have the same as in the state psi. And before that point, we have the same as in the vacuum. Okay, and it's clear that in this history, the integral of the stress tensor along this dashed line is going to be negative, because we have the negative contribution, but not the compensating positive contribution. And, well, this sounds funny because we have negative average null energy, but it's totally fine with the theorem, that the average null energy condition, because the assumption of that theorem is that we have a local relativistic quantum field theory. And here, when we use a Hamiltonian that involves a non-local coupling between these 2 points, we're breaking the rules. We're breaking the rules of local relativistic quantum field theory, and so it's perfectly okay that we found, as a result, a history which has negative average null energy. Okay. So now what we're going to do is we're going to combine these two sort of preliminary parts of the talk, this discussion of the thermofield double wormhole and the negative energy, in order to make a traversable wormhole. So this is what was discussed in the paper by Gao, Jafferson, and Wall. And here's how it works. We start by thinking about the thermofield double state. Let's evolve this diagram up from the bottom to the top. So we start with the unperturbed thermofield double state here. Then at some time, we act on the right to send in some kind of a signal, some message, which normally would not make it to the left side. Then at t equals 0, we interrupt the evolution of the system by acting with this operator here. That creates some negative energy in the bulk. And when our signal encounters that negative energy, well, here we're drawing the diagram in the way where it just has a null shift as it crosses this blue negative energy. The null shift is now in the opposite direction from what we had before, because the integral of t minus minus is negative. So, okay, so now the trajectory can actually go from the right side to the left side, and we've made the wormhole traversable. Okay, so I'm going to make four comments about this. The first comment is just sort of to get the sequence of events straight. It's helpful to think about this protocol as like an emergency protocol that could be followed in a factory for preparing thermofield double states, in the unfortunate circumstance that one of the workers falls into one of the black holes. So here we have the black hole. It's being prepared for the thermofield double. The worker falls in. They despair. They think that their fate is sealed. They're going to die in the singularity. But they have very capable coworkers who are still outside the black holes. And the coworkers realize that if they wait a little while and then they act with this if they act with this operator, then they'll create a puff of negative energy inside the black hole, and their previously unhappy coworker will emerge safely into the asymptotic region of the left black hole. Okay. Okay, second comment. There's something that seems sort of funny about this, which is that we're discussing here a quantum effect involving only a few quanta. We should think about acting with just maybe a few of these O operators, and somehow it's having a significant effect on the whole space-time structure of the geometry that we're considering. To put it another way, it looks like any effect, the negative energy associated to these operators should be of order 1. So the back reaction of that on the geometry should be suppressed by g Newton. So it should be a very small effect. But it's having an important influence on the discussion. You can sort of see what's going on, because if we make this time very early, then even a tiny little kick in the null direction will be enough so that it will make it to the other side. In other words, we started with a configuration that was almost traversable. So even a very small amount of negative stress energy is able to make it actually traversable. A more invariant statement is that the wormhole becomes traversable when this small back reaction parameter g Newton multiplied by this exponential function of the time separation of these operators, so this time t, when that combination becomes of order 1, the wormhole becomes traversable. And this is a combination that we recognize now as being associated to chaos in the CFT description of the system. So the CFT explanation for why just adding a few quanta like this can have such a big effect is that if we wait for a scrambling time, logarithmic in g Newton, then these few quanta can have an important influence on each other because of the amplification of few particle effects by chaos. Okay. So the third comment is the following. Sometimes people are a little bit dismissive of this effect because they say, look, you've taken the two systems which were separately initially decoupled, and you've added an explicit coupling to the Hamiltonian. This O left times O right term is a coupling between the two systems. Why should I be surprised that it is then possible to send information from one system to the other? Okay. And the people who say that are, in some sense, justified, because indeed it's possible now to send a signal from one side to the other, precisely because we've added this coupling. But there's something which you're sort of missing if you think about it too simply, which is the following. The two-sided coupling makes it possible for quanta of the O field to travel, sort of to be annihilated here and created here. So that term allows this type of trajectory for the O quanta. So in an obvious way, it allows particles of the O field to travel from one side to the other. But we can imagine that the signal we're sending is in the phi field, which is a completely different bulk field, coupled to O only through their mutual coupling to gravity. And this coupling does not allow the phi quanta to pass through, only the O quanta. And indeed, the phi quantum is not passing through in some obvious stupid way through this coupling here. It's passing through the interior, through the wormhole. So the interesting point here is not so much that you can send information from one side to the other, it's how that information gets sent. It gets sent through the wormhole as opposed to through this more obvious boundary coupling. Okay, now the fourth comment has to do with the relationship of this protocol to quantum teleportation. So quantum teleportation is a protocol for doing the following. I want to send you a quantum state, but we're only allowed to communicate classically. So if we share an entangled state, then it's possible for me to send you a classical message based on a measurement of my quantum state, and for you to reconstruct that quantum state on your side after you receive the message. So we can make this traversable wormhole thing look a lot like quantum teleportation with a small modification. So instead of applying our operator here, what we can do is something else. The person on the right side can measure OR, measure their half. They'll get some result, some number result, OR, little OR. Then they can send the result, little OR, to the left system, and the person on the left system can apply this operator. You'll notice that this is now just an operator acting on the left system, because it involves the O left, but only the number OR. And from the perspective of the left system, this has exactly the same effect. So the space-time diagram for this is a little bit different, because the measurement that happens here will in general add some positive energy flowing in from the right side, but we'll still have negative energy on the left, and that's all that's important for getting this signal to travel from the right side to the left. So in this presentation, it's very similar to quantum teleportation. We want to send the quantum state, which is encoded in this phi field. We send only classical information, which is the result of a measurement here, but because of the previous entanglement between the two systems, which is represented here geometrically by the wormhole, it becomes possible for the quantum signal to make it to the other side. Something that Juan Maldacena likes to emphasize about this is that it's an extremely comfortable form of quantum teleportation. Normally when you think about teleportation, not even just quantum teleportation, just classical teleportation, that sounds like something that you wouldn't sign up for, because it involves some kind of a complete measurement of yourself, and then maybe a reconstruction later in some other place. But here we can see what happens to the information that's being teleported, and it has a completely pleasant experience. It feels to the information like it's just in free fall through an empty wormhole. It encounters a small puff of negative energy, but this can be made to be completely drama-free. And so this is a type of teleportation that you could sign up for. It's like a luxury version which uses black holes, but there's no complete measurement of your body. Okay. So now, in the remaining, 15 minutes or so, I'm going to discuss a limited application of this discussion, these traversable wormholes, to the black hole information problem. So before we do that, it's going to be helpful to be working in a slightly simpler framework where we don't have to discuss negative energy explicitly, and where the gravitational dynamics is basically trivial. And that will just make the discussion a little bit easier, although it's quite general. So that framework is two-dimensional gravity in ADS, in anti-de Sitter space. Now, two-dimensional gravity is weird. If you just write the Einstein-Hilbert action, you get a topological action, which doesn't lead to interesting dynamics for the metric. But a reasonable action to consider in two-dimensional gravity, which is closely related to what you get from compactifying from higher dimensions, is this. It's called Joukhiv-Teitelbaum gravity. It involves a dilaton scalar field coupled to the metric. This is the action. You can see that if you integrate over the dilaton phi, that will set r plus 2 equal to 0. So that means, in two dimensions, that means that the geometry is a piece of rigid anti-de Sitter space, of rigid ADS2. But it doesn't tell you exactly which piece. So the degree of freedom in this theory is the location of the boundary of the part of ADS2 that we're looking at. So this is a very simple theory of gravity. The dynamics for this particle that tells you where the location of the boundary is, the world line of the boundary, the dynamics for that is equivalent to a particle moving in an electric field in rigid ADS2. So this is what this theory of gravity reduces to, just the motion of a particle in an electric field. So here's a simple solution. So here's all of ADS2, and here I'm drawing the world line of the boundary. In this case, we actually have two boundaries. They're uniformly accelerated because of the electric field. And this is a solution to the Joukhiv-Teitelbaum model. What this looks like is the thermofield double state. So you'll notice, so this is the right boundary, this is the left, and you'll notice the familiar fact that if we act on the right system, we can't send a signal to the left, simply because the left boundary is accelerating away from us too fast. And this is really a description of a black hole in two-dimensional anti-de Sitter space. Okay, so how can we implement this traversable wormhole in this simple theory? Well, if we act with this operator, O left times O, e to the ig, O left times O right, this can be approximated just by adding a term, adding the expectation value of this term, viewing that thing as a potential energy, as a term in the potential. And okay, that potential, the expectation value of these guys depends on how far apart they are, how far apart the two boundaries are. So if we think about this potential as a function of the separation between the boundaries at some curve that looks roughly like this, if g is positive, in particular, you'll notice that it's an attractive potential. It's an attractive potential between the two boundaries. It wants them to be closer together. Now, acting with this at a particular time is like adding this term to the potential with some delta function of t. So it's like an impulsive force. So this potential is turned on only for an instant, and it creates an impulsive force. That impulsive force has the effect of kicking the trajectories of these boundary particles towards each other slightly. So that's indicated by these arrows. And now, of course, you'll notice that if we send a signal from the right boundary, it can make it to the left. So this is just the translation of what we've already discussed into these simple variables. Okay, so now we would like to move to thinking about black hole information. So let me just review briefly this by now classic result of Hayden and Preskill from 2007, where they were discussing, under the assumption that a black hole evaporates unitarily and that its dynamics is rather mixing, they show that you can extract information about what fell into a black hole before it's completely finished evaporating. So the setting here, so imagine, let's just draw a diagram for a black hole in flat space. It collapses. There's some collapsing matter that forms the black hole, and then there's a bunch of Hawking radiation. Eventually, the black hole evaporates completely. So let's go halfway through the evolution of the black hole so that half of it has evaporated into Hawking radiation, but there's still a reasonably large black hole remaining. And at that time, let's imagine that we have somebody called Alice who throws her diary or some message into the black hole. Now, we also have Bob, who's outside the black hole with a huge quantum supercomputer, and he's been collecting the first half of the Hawking radiation and storing it on the hard drive of his quantum computer. His goal is to recover Alice's diary. Now, the remarkable thing that Hayden and Preskill show is that he can recover Alice's diary using his half of the Hawking radiation plus just a few more quanta that come out after Alice throws her diary into the black hole. So he needs a few more quanta plus the first half. And then under some assumptions, well, like for example, that black hole evaporation is unitary and the dynamics is scrambling, they show that he can then recover a second copy of her diary. Now this seems, yeah, the second copy is indicated here in red. And here I imagine that after he extracts it from Hawking radiation, he jumps into the black hole. This is immediately hugely problematic because we have two copies now of the same quantum information in the diary. And to make things worse, we can imagine that after Alice's diary falls in, maybe it's falling in with a rocket that turns it around. After it falls in, it travels in this direction. So actually, Bob, with his copy, can intersect in space-time the other copy, and he's sitting there with a cloned copy of Alice's diary. And this is something that's impossible in quantum mechanics. So this is really a puzzling feature of attempts to understand how you get information out of black holes before they've evaporated. But we can try to understand this using our traversable wormhole. So here's how this works. We're going to make a model for the black hole after this halfway evaporation point. We're going to model it as a highly entangled state, the thermofield double state, where we interpret the right half of this system as the actual black hole, and we interpret the left side of this system, which is maximally entangled with it, we interpret that half as being the first half of the Hawking radiation, which, if you like, has been collapsed into a second black hole, which is entangled with the first one. Or if you don't like that as much, what you can imagine is that the first half of the Hawking radiation has been stored on the quantum computer that Bob is holding, but he's using that quantum computer to simulate a black hole, so that this is like a second asymptotic region. Okay, so this is our setup. We're going to use this wormhole to try to understand this problem. So now if we just repeat the steps, we're already at the halfway point when we discuss this state. We imagine that Alice throws her diary into the black hole. That's the red trajectory there. Then Bob waits a while, and what he does is he does this teleportation version where, let's say, he measures a couple of quanta from the right side. That's like gathering a couple more Hawking quanta from the evaporating black hole. So he just gathers a couple of these Hawking quanta, he measures them, and then he makes the corresponding operation on the left side that we discussed before. That creates some negative energy, and now Alice's message propagates from the right side to the left. So in other words, the message propagates into his quantum computer. Now in computer science and in quantum information, people have to go through all these hoops of trying to validate their algorithms. And I mean, this is how we validate algorithms in geometry. It's really remarkable to see the success of this protocol. You just follow in space-time the trajectory of the diary, and you see that, in fact, it just propagates locally into the system that's the quantum computer. So that's how we see the algorithm has succeeded, and Bob has recovered Alice's diary. So this is exactly analogous to the Hayden-Preskel setup. So we should try to understand what happens with cloning in this version. So OK, here's how we do this. So now I'm going to draw Bob's world line. He's the one who's controlling the quantum computer. Draw his world line in black. So here he is. At this time, this is when he makes this operation. And then he continues monitoring the quantum computer. And at this time here, Alice's diary becomes available to him in the memory of his quantum computer, or the asymptotic region of this second black hole. So he has two choices at this point. Choice A, he doesn't extract Alice's message from the hard drive. He leaves it there. It bounces off the boundary and returns into the black hole. Then, if Bob likes, he can travel across from his quantum computer and jump into the actual black hole from the right side. He's not carrying Alice's message, so when he falls into the black hole and finds it inside, he won't be surprised. He won't have experienced any quantum cloning. Option B, at this time, he extracts Alice's diary from the space-time. He extracts it from the hard drive of his quantum computer, and then he carries it with him when he moves over and jumps into the black hole. So now the red line is following the black line. Then when he jumps into the black hole, he's carrying Alice's bit, but you'll notice that he doesn't find a second copy behind the horizon because his extraction step here removed it from the space-time geometry. So the traversable wormhole is giving us a geometrical realization of this Hayden-Preskel algorithm, where we can see that the algorithm succeeds, but we can also see that the operation that you do to extract the diary from the Hawking radiation, that's this step here. So the left side is like the Hawking radiation. The operation that you do to extract that removes it from the region behind the black hole. So there's only ever one copy of the diary, and there's no cloning. So we would like to understand, well, this is an extremely special case where we're modeling the Hawking radiation as a second copy of the black hole in the thermofield double state. What one would like to do is understand how this is supposed to work in a more general evaporating black hole. And this is a challenge. I don't really have anything intelligent to say about this, except one possibility is sort of a qualitative change in my view of how information is supposed to emerge from black holes. So the way I used to think about it was that if the information falls into the black hole across the horizon here, then it has to come out by recrossing the horizon at some later time along some, weird acausal trajectory. But I think what this traversable wormhole picture suggests is a different type of space-time diagram where the message falls in, and then it enters into the mouth of a wormhole here that is connected to the Hawking radiation. The wormhole connected to the Hawking radiation, and it emerges into the Hawking radiation through the wormhole, not by recrossing the horizon. Now, we have no understanding for why there should be a wormhole connecting the Hawking radiation to the interior of the black hole. That was basically the content of this ER equals EPR conjecture of Maldacena and Susskind. And until we have a detailed understanding of that, we won't understand whether this is viable or how the information escapes from the black hole. But this is my hope. This is my hope for how it does it. OK, I think I'm out of time. I'll just put my summary slide here. You guys can read it if you want. Well, thank you very much for your attention.
We're sure there will be a lot of questions. Jim, first of all.
I think we're going to hear a little bit later in the morning about another method, soft super rotation charges for getting the information out. And here we have ER equals EPR for getting the information out. Are these ideas connected? Are they compatible?
As far as I know, there isn't actually an idea for getting information out of black holes using the BMS charges. My understanding of this is that the soft gravitons are an additional complication when discussing Hawking radiation in four-dimensional black holes in four-dimensional asymptotically flat space, which complicates the final state of the Hawking radiation because it's in a space with Hawking radiation and also clouds of soft gravitons. But that doesn't actually give an explanation for how the information gets out of the black hole. It just says that after it's out of the black hole, it gets sort of dressed up in a complicated way by these soft gravitons.
Thanks.
Faye, over there.
I think what you've described is a very sophisticated example of something very simple, which is the following. If you have two space-like separated systems, to say 2 qubits, and they're in an entangled state, and if you're able to do a non-local unitary operation on the joint system, or a measurement, for example, of a non-local observable on the joint system, then that will enable superluminal signaling between the two space-like separated subsystems. And it's been pointed out by many people, including Raphael Sorkin, in a paper called Impossible Measurements on Quantum Fields. So the conclusion that Sorkin and others have made is that this non-local operation, measurement or unitary transformation, is impossible because if you could do it, then you would get superluminal signaling. And I think that's what you have here. You're making this operation which is applying, you keep saying applying e to the I, O left, O right, or something like that, to the system. If you can do that, that's non-local. I mean, so if you can do that, then it's not surprising that you will get it's not just superluminal influence, but superluminal signalings between the two space-like separated subsystems.
Yeah, that's right. So if you make so here we're playing by rules where we're allowed to act with an operator that couples together points at space-like separation. And because of that, it's not surprising that information can get from one side to the other. What's surprising is how it gets from one side to the other. It goes through the wormhole. Now, you could say that this is crazy to ever consider such a situation. But actually, ADS-CFT gives us a very well-controlled environment in which we can discuss it. So that environment is, well, we can think about the two quantum mechanical systems that are the ADS-CFT systems. And then those are just some condensed matter systems or running on a quantum computer or sitting in the laboratory. And they have an emergent description of an anti-de Sitter space with the black hole. But we can imagine within the laboratory technicians can couple those two systems together. And so that's a physical implementation where we can have this coupling between the two systems that's sort of, well, that's exactly the coupling that was described here. An O left in the left CFT times an O right in the right CFT. The surprising thing that happens then is that the information that travels between the two sides goes through the wormhole that's being described by the two systems.
I think if you have time, I'm going to suggest that questions, I'm sure there are many, including Andy's, could be left for coffee break because
maybe I'm afraid that I might have said something that Andy's not happy with. Maybe we should allow him to make whatever comment. Oh, sorry, Andy, you should make whatever comment you wanted to make. Yeah.
Did want to ask, which is if you want to rescue your coworker, can it be a macroscopic coworker, or does the coworker just have to be a few quantum bits?
Yeah, this is a great question. So, If it's a macroscopic coworker, then what you need to do is you need to act with lots of these O left times O right operators, as many as there were quanta in your coworker.
Okay, I think we should move on. There will be lots of time for discussion over coffee, so let's thank the speaker again.